All right, welcome. So what I'd like to do is illustrate a few of the things that I've done in class. So you've done the patterns lab. Now, there's a purpose for the patterns lab. This is what I'm talking about. I have a paper copy. It's called the patterns lab. It's available on the document where you can link to this video. But basically, here's what happens. I have a picture kind of like this. And this particular picture has 6 blocks in it. And this represents the first picture, or the first scene of a situation. This is the second scene, and this scene has 7 blocks, and this is the third scene, and this scene has 8 blocks. So what's happening in this picture is, in each successive picture, I'm adding one more block to what we call the tower. So in order to track this pattern and see how things are growing, I have a chart, or a table here. On the left side of the table, I have how many cubes are in this tower, so this top part of the picture, and then how many cubes do I have in all that I'm using. So this first one I have 6 cubes, in the second picture I have 7 cubes, and in this third picture, like I said, we have 8 cubes. So if you're just looking by how this is growing, going down the side here, I'm just adding 1 cube every picture, okay? Well, the question would be then, how many cubes am I going to have in my 10th picture? Well, in order to find that out, if I continue this pattern, I would have to do this pattern about 10 times before I figured out the 10th picture. That's doable, right? But what about if it's 100 times? Well, that becomes a little more cumbersome. So what we want to do is we want to find a shortcut, some way to determine if I give you the tower number, or what picture I'm on, how many cubes are going to be in that particular picture. So in this case, instead of looking down on the right side, we're going to look across from one side of my table to the other. So from 1 to 6, 2 to 7, 3 to 8, and so forth. So a couple tips here. The first tip that I find is, first thing I try to do is, can I add or subtract? Adding or subtracting is a very common way to create a pattern. Just like here, we added 1 every time we went down. All right? Well, 1 to 6, well, that's 5, right? So if I add 5, that gets me to 6. 2 plus 5 is 7, so that works as well. And then 3 plus 5 is 8, so that also works. So it looks like the pattern here is I simply add 5 to the number on this left side, to the number of cubes I have in the tower, and that'll tell me how many cubes I have in total. All right, so 10 plus 5 is 15, 100 plus 5 is 105, and then just a general pattern, a way that I could always remember this, I would write n plus 5. If I picked any random number of cubes in my tower, I'd always know. I just add 5 to that, and that'll tell me how many total cubes I have. And this is quite apparent because if I have 1 in the tower, there's these 5 at the base, and those are consistent. These 5 here in the base, these 5 in the base, they never change. The only thing changing is how much I'm adding in the tower. So that's a relatively easy pattern. The second step I always ask myself is, can I multiply? Well, having trouble spelling today. Multiply. All right, so can I multiply? So this particular problem comes from problem number 3 in this patterns lab activity. And so the picture, if you look at the picture, which I don't know if you're going to be able to see, but the picture is 3-dimensional, which is why I didn't draw it. But it says a tower with 1 floor takes 3 cubes to build. So this is the number of floors in my tower, and it requires 3 cubes. This is the number of floors in my tower. It says that with 2 floors, it takes 6 cubes to build, and with 3 floors, it takes 9 cubes to build. So again, if I keep going down this way, I'm adding 3 each time. But if I want to get to 100, I'm going to have to do that 100 times, and I don't really want to figure that out. So what I'm going to do instead is I'm going to go across. So 1 to 3, 2 to 6, 3 to 9, and I want to figure out if there's a pattern. Now if I add, right, if I do adding or subtracting, I add 2, and that gets me 3, that's fine. But if I add 2 to 2, I get 4, not 6. So adding doesn't work. So let's try multiplying. So can I multiply? Well, 1 times 3 is 3, so times 3 is 3. 2 times 3 is 6, that worked. 3 times 3 is 9, so that worked as well. So it looks like the pattern here is I'm just going to multiply by 3. So 3 times 10 gets me 30. 3 times 300 gets me, or 100 gets me 300. And then 3 times n, so that's 3 times n, right? That's not bad. That's a pretty good, decent pattern. So this is an adding pattern. This is a multiplying pattern. Now I want you to bear in mind that the pattern here was adding 3, and I ended up multiplying 3 to get across. So that's going to come back to us in a moment. So let's try this one right here. This one is problem 6 on your packet. So the next thing is, can I add or subtract? Can I multiply? So the last thing you want to ask yourself is it a combination of both? All right, because sometimes it is a combination. And so check this problem out. If I look here on the left side, what we're doing is we're taking, and I'll show you the picture again to see if this makes any sense. We're taking cubes, and we're going to enclose a single cow in this pasture. So if you look here, I don't know if this is visible, but 1 cow in the middle of this fence, 2 cows in the middle of this fence, and 3 cows in the middle of this fence. And we want to know how many cubes it takes to get that fence. So yes, this is kind of a silly example, but the principal concept that we get from studying these patterns will really help us as we get into linear functions. And I'll explain that in another video. But for right now, let's focus on these patterns. So if I had 1 cow, they said it would take 8 blocks to get around, or 8 cubes to make my fence. If I had 2 cows, it would take 10, and if I had 3 cows, it would take 12. All right, so far it looks like a simple pattern, right? If I'm going down the side, I'm just adding 2 each time, right? I'm adding 2, I'm adding 2. All right, but like I said, in order to get to that 100, we'd have to do that 100 times, and I don't want to do that 100 times. So what am I going to do? Well, let's look across and see if we can find any noticeable patterns. So first things first, can I add? If I add 7 to 1, that gets me 8, so that works. But if I add 7 to 2, that gets me 9, and so that doesn't work. So we're not going to add. So can we multiply? Well, 8 times 1 is 8, but 8 times 2 is 16, so that doesn't work either. So we're kind of stuck. And I guess what we can do is it a combination of both? So here's what we're going to do. You see how down here in this pattern, I added 3 on this right side, but when I went across, I multiplied this number on the left side by 3 to get across, and that became my pattern. So let's take a clue from that. I'm going to multiply all these numbers by what I added down and see if that works. So multiply by 2. Okay. So 2 times 1, that's 2. It's not 8, so that doesn't work. But I'm going to keep track of that. So 2 times 1 is 2. 2 times 2 is 4. All right, well, 2 times 3 is 6. And again, none of those 3 numbers equal those ones. Well, here's my third question. Is it a combination? Do I have to add something else? So now that I've multiplied, let's do a combination. Let's see, what would I add in order to get there? So far, I'm multiplying by a common number, right? That adding 2, I just multiplied by that 2. Okay. What do I add to 2 to get me to 8? So I add 6 to 2, and that gets me 8, right? What about from 4 to 10? Well, 4 plus 6 is also 10. Oh, that worked. See, I added the same number, and I got the numbers I needed. So let's try that again. So if I do 6 plus 6, that gets me 12. So this is brilliant. What's happening here is my pattern ends up being multiply it by 2, and then add 6. So this is 20, and then plus 6. So this gets me 26. Or multiply this times 2, that gets me 200. And then I add 6, so that gets me 206. All right, so my pattern, times 2, so n times 2, and then plus 6. Well, that's nice. But where did that 6 come from? Is that random? Did I just pick that? So check this out. There is an easy way to get this. So far I know that if my pattern is adding repeatedly, okay, if on the right side I'm adding 3, I'm adding 3, I'm adding 3, and that's how I'm increasing the right number, then it looks like I'm going to multiply by that number going across. So where does this 6 come from? Well, check this out. If for 3 cows I had 12, I need 12 blocks. For 2 cows I needed 10 blocks. And for 1 cow I need 8 blocks. So this, if I'm going backwards by 2 each time, what would happen if I had 0 cows? Well, you wouldn't need a fenced-in cow port, would you? But let's just think of it hypothetically. So if I continue this pattern going backwards, 12 to 10, 10 to 8, it would be 8 to 6, right? That's the exact same number I added on this side. So we're getting these pieces from 2 different parts of my pattern. I'm getting it from the adding pattern that I would normally do if I just wanted to get the next term, and also what happens if I went back 1. So if I was doing this backwards, 9 to 6, 6 to 3, I would subtract 3 and I would get 0. So there'd be 0, 0, which is why my pattern here, I don't have to add anything to it. Okay? Well, what about this one? I'm adding 5, right? If I go backwards, 8 to 7, 7 to 6, and if I had 0, 6 to 5. 5 is that number right here. But wait a second. If I go down, I'm adding 1 every time. How does that factor into play? Well, over here, I multiplied by 3, right? And over here, when I went down by 2, I multiplied by 2. Well, n by itself is just 1 times n, and it doesn't change anything. So what do we get from this? If I have a pattern, all right, or a table of values, let's say I have a generic table of values, okay, and it goes something like this. And this would be number 7, and it has a context, but I'm not going to read it. I'd like to bring this back to how this relates to linear functions. If I have a table of values, I can create that function just by using what we found with these patterns. So what's the pattern here? Well, 7 to 11, 11 to 15, I'm adding 4 each time, right? And then if I go backwards, the 0 term, and I should probably make some room here, but the 0 term, so if I went back 3, 2, 1, 0, and I went 15 to 11, 11 to 7, 7 to, if you subtract 4, that's 3. So where did I get from this? Since I'm adding 4 each time, if I go across, I would do n, so n times 4, and then I'd add the 0 term, so plus 3. So my formula here would be 4n plus 3, and that would be my explicit function. It's not bad, huh? So that's going to be important as we go along, and I'll show you the purpose of these 2 numbers. It actually falls in line with this formula, which is a linear formula. All right, look familiar? The only thing this is missing is the y portion, okay? So anyway, I thought I'd let you see that and see how that rolls, and we're going to move on to a different topic, okay?